Hi, my name is Shad, and I'm going to be your teacher and guide today for this course on software reverse engineering. So that's the technique of taking code that's already been compiled and reversing it into something that you can manipulate. So that means you might see the source code, or at least you will be able to see the assembly language and then make any modifications or understanding of what the program is doing. So this course is taught in 8 pieces. In part 1, we'll talk about numbering systems. So if you have not seen binary numbers or hexadecimal before, this will give you a great start into how you can understand what a reversed piece of software looks like. Then we'll do some experiences to get you used to the idea of software reverse engineering, the first attempts. Then we'll have a session where we compare the different tools that are popularly available. And of course, we're looking for free tools, but there are commercial ones as well. And then we'll talk about the reading the stack feature. So this is understanding a program as it's running and doing some debugging while it's in action. Binary patching is about taking a piece of software and modifying it, even if you don't have the source code. And so you can patch things to fix errors or to maybe bypass a certain feature like a login screen or a registration screen. Recognizing code patterns will give you a more in-depth advanced feature of how you can see maybe malware and diagnose what it's doing. And that's this video here right now. And then anti-debugging techniques is the ability to take a piece of software who is trying to hide from you. So this is a cybersecurity topic where we are looking at software that knows that you are reverse engineering it and you're trying to avoid that. And then finally, we'll do some fuzzing techniques. So this whole course here is about software reverse engineering. Now, the guides that are going to take us through here are from Dakota State University. So Michael Ham and Andrew Kramer are both the teachers. So let's get started with this section right now on software reverse engineering.
Other tools, and then I'm going to show you the code. You'll try and draw the flow chart. Then I will compile it and open it in IDA, and we'll see how close you are. So I would like this to be kind of interactive and hands-on and fun. So if you have a piece of paper and a pen, get those out. I'm going to show you some C code, and I want you to try and draw up what you think the graph will look like when we compile this and then open it in IDA or one of those other graphing disassembler tools. So there's your C code. I'm going to give you just a minute to look at that and think about it and work on it. And while you do that, I am going to type this up, I'm going to compile it, and hopefully by the time I have it open in IDA, you have an idea of what this will look like. I'm going to compile it like M32 and then just the C code, just like that. So whatever the defaults will be, optimization level 1. Oh, keep it very simple. I mean, think about this not in terms of the assembly code that it's going to produce, just the logic. So if your block says if A is greater than 10, that's a block of code, right? You'll see when I show you one example, and then the rest will be easier. And then, once we're done with a few of these, we'll do it in reverse. I'll show you some IDA graphs, and you'll try and write the C code for them. Okay, so let's start with this. I'm going to, let's see, cd desktop. Let's do make directory examples. So we'll call this if.c. And of course, this program doesn't do anything useful, just an example. Whoops, sorry, I'll bring that right back up. Okay, let's go ahead and do this one. So I'm going to fire it up in IDA here. I have another slide. Whoops, too many things open at once. I have another slide with what I think I would have drawn if I was going through this activity, and that is something like this. So we're not going for exactly the assembly code that the compiler is going to produce, but rather just the structure of the control flow graph of what that's going to look like loaded into IDA. So I have if A is greater than 10, that's a condition that we're checking. We have two arrows coming off of that for true and false, indicated here in green and red. If the condition is true, we go to A++. If it's false, we go immediately to return 0. So I'm going to open this up in IDA now, and let's take a look and see if that's what we see. So, can I zoom in? Oh yeah, but it's very delicate. I'll do my best. If that is what you drew as well, you nailed it. Good work. How many people have an accurate control flow graph? Okay, so let's add to this then. We're gonna keep adding a few other things here. So your next challenge is to add an else statement to that graph. So here we have an if and an else. And again, I'll give you a couple of minutes. I'm going to write this up in C, compile it, then we will open it in IDA and see what it looks like. Okay, let's go ahead and see what this graph looks like. So I'm going to show you what I would have written, and this may or may not look similar to what you have, and then we'll see what IDA says. So here's what I have. We have our condition up at the top. We have true and false branches. Well, true and false and true. In the false case, we have A minus minus. In the true case, we have A plus plus, and then both of those converge at the end again with a return 0. So an if-else structure should kind of be this conditions and then convergence at the end. So let's open that up in IDA and see what it looks like. And then click through all the error messages. Someday I'll Google those and figure out what's going on. Okay. And there we have it. I think that is a close match, if not an exact match. That looks good. Trivia question. Can anybody tell me why there are 2 lines of assembly code in this condition and only 1 line of assembly code in that one?
It just falls through.
Yeah, we need that extra jump there in the linear assembly output, right, in order to jump over the second condition, but IDA has included that as part of that.
Linear view time?
Yeah, we can hit spacebar. We can check it out. Let's see. There we go. There's the assembly code. Good. Okay, let's make it a little bit more complicated then. So here we have an if-else statement. And see if you can draw up a control flow graph for that. I'll give you a hint. 1 block with 3 legs. It's not. Hans and Logan are writing assembly code out. Push EVP, move EVP, ESP. Okay, so here's what I think this will probably end up looking like in IDA. Up at the top, we have an if statement. If A is greater than 10, that branches into 2 options, true or false. If it's true, we're going to add 1 to A and go to the end. Otherwise, we have another chance to take one of 2 paths. If this statement is true, we set A equal to 0 and go to the end. Otherwise, subtract 1 from A and go to the end. So let's take a look at this in IDA now, and let's see if that graph matches up with what we thought. So I'm going to close that one, open this. Okay. And here we go. So I probably won't be able to zoom in on this one too close. That's about as good as I can get it. So let's walk through the assembly code line by line on this one. I'll go quick, just so we can see what's happening. So I see a compare var4 to A. What is A in this case? 10. Yeah, that's a hexadecimal 10. So one of the things that I like to do when I'm reverse engineering code is change the type so that they look a little bit more like what I would expect in the C code. That might be changing it to a character or changing it to a decimal number depending on what's going on. And if that variable 4, which we could rename to say like a variable called a, is less than or equal to 10, then we're going to jump to this block. Less than or equal, of course, is the opposite of greater than, so that's like a not greater than. In this case, though, we compare a to 0, and we have a j in s. Anyone know what a j in s instruction is?
Jump not signed.
Yeah, jump not signed. So to understand what's going on with that jump, you would have to look at the flags register and know that there is a sign flag that gets set when the result is negative. I don't want to go too deep into the internals of those x86 instructions, but basically that's checking for a negative result, right? And so again then, either we're going to move a 0 into A, or we're going to subtract 1 from A, and then in all of those cases, we end here at the end. How many folks drew up a control flow graph that looks close to that? Feel good about it? Nice, good. Okay, I have, I think, 2 more for you here. Actually, maybe 3 more, but kind of 2. Okay, so here we have a for loop. I have 2 variables, a and b. For a equals 0, while a less than 10, a plus plus, and in the middle, b plus plus. Ready, set, go. Okay, let's take a look in IDA. Let's see what this looks like. So I have already compiled the program. I'm going to open it up with IDA. Let's just say, don't display this error message again. Good enough. And here, we'll just make it full screen. Sorry, folks, the zoom in is so sensitive here. No, not quite. There we go. That's probably as good as it's going to get. So that stuff up at the top, the call x86 get PC thunk AX, which I would hope and assume Logan and Hans have implemented in your, you've compiled in the get thunk, right?
Yeah.
Good, yeah, okay. We'll just hide that. We don't need that. So up at the top, I have moved to EBP var 8. Remember, we had 2 variables this time, so we're going to have var 4 and var 8 for our A and B variables. I have put a 0 in var 8. Which of those 2 variables, A or B, do you suppose var 8 represents? A. Yeah, that's going to be our loop counter, right? We can see a 0 being put in there at the beginning because that's what we need to do before the loop begins. And now I have 3 blocks of code below that. I have a comparison, comparing var 8 to 9. So that's something interesting to note as you're thinking about how these structures in IDA sort of reverse backwards into the C code. In the C code, I wrote less than 10. The compiler chose to change that to less than or equal to 9, which is functionally identical, right? There's no difference. They're the same thing, but the compiler chose to do it a little bit differently. So 6 of one, half a dozen of the other. In the true or false cases, so in the true case, we're going to add 1 to var 4, which would then be our B variable, our second variable, and then add 1 to var 8, that's our A variable, our counter, and loop back up to the top. Otherwise, in the false case, we hit the end of the program. So something interesting that IDA does with this for loop is it draws the actual loop, the loop arrow, around the end of the program, right. Which I think if I was drawing this out on paper, I would not draw it around the end. But same difference again, right? It doesn't actually matter. So, I don't know, topologically, is that the right term? Does that match what you all drew up as well?
So what's the reasoning behind having the first jump there and not just saying move, compare, and then...
Ah, this is a wonderful question. Did anybody else notice that? There's a jump to the next block of code. So this refers back to what I said a moment ago, that depending on how much assembly code you've written by hand, you might structure this a little bit differently. I'm going to switch to linear disassembly view, and let's see if we can figure out why there's a jump rather than just falling into that first block. So hit space. Can I zoom in? It does not appear so. I'm not sure I can zoom in here. Can you all read that, or is that too small? So I'm going to let you just look at this for a few seconds here and try to figure out what the compiler has done. It's maybe a little bit clever. Why is it that that jump at line 11A4 exists? Why is that necessary? So in the C code, would you call that a top tested or bottom tested loop? Top tested, right? A for loop is top tested. The test happens before the body of the loop. In the assembly code, does the test exist before or after the body of the loop? After. After, right? The compiler moved the test down to the end. Look right here, the two adds. This is the body of the loop. Add one to B, add one to A. So the compiler took what should have been a top tested loop and moved the test down to the end. So how did it still accomplish a top tested loop behavior when it has the test at the bottom? The first thing it does after putting 0 in the variable here is jump to the comparison. Now, why does it do this? Compilers are magic, right? So there's a couple of reasons I can give you. I'm not super confident in my answer here, so don't quote me on this. I think it probably helps a little bit with branch prediction to have the comparison at the bottom. Like there's some efficiency gain in the way that the CPU is going to pipeline the instructions or something. I also think it means that you have to have, well, wait a minute, I was going to say have one less branch instruction. Oh, so if it's the other way, if you have the comparison at the top and then a jump at the bottom to loop back up, then you have 2 branches per loop iteration, whereas here you have n plus 1, right? Here you only have 1 jump per loop iteration and then 1 extra at the end. So you get less branch conditions per loop iteration and some CPU efficiency in the background. And I don't understand enough about CPUs to say any more than that. I'm sure some of you with maybe a little bit more computer engineering background than I could. I'm going to do something a little bit different for this next one. I'm going to save this window. I'm going to leave that one open. And then I think I'm going to open a second IDA window, open a new instance, and I'll show you why in just a minute. We'll do that in a second. So, yep, that's what I think the graph would look like. The blue line could go around the end there. Same difference either way. So I want you to look at this code now and see if you can write up or imagine what IDA is going to do with this code. And while you do that, again, I'm going to type it up, I'm going to compile it, and then I think we're going to see something interesting happen. Some of you may already have an idea what's going to happen here. It should be basically the same as the last one, right? A for loop versus a while loop is really just syntactic sugar at the C language level. Functionally, these are basically the same. As far as order of operations go, we're going to put 0 in our A variable. We're going to check the condition if A is less than 10. If so, increment B, increment A, which like this would have moved over here with the for loop, and that would have moved down, and then return 0 at the end. So this is structurally the same code, just written using different syntax. And in fact, it's kind of interesting, I have compiled that, and I've opened it with IDA, and I want to compare and contrast the two. So this here is the A2 binary. Okay, I'm going to get it right. Almost. There, perfect. That's A2. And this is A1. The one on the left was built using a for loop. The one on the right was built using a while loop. These are different pieces of C code compiled into different binaries. Can you point out any differences between the two? they are literally the same, right? At a compiled assembly code level, and at the way that IDA looks at it, this level, they're exactly the same. So I tell my students, if you see code like this, and I ask you, is this a for loop or a while loop? The answer is yes. It is a for loop or a while loop. Okay, let's do one more like this, and then I'll let you do the same in reverse. We'll look at some graphs and try and write the C code. So your last exercise here, before we change gears, is a do-while loop. So still loop structure. A still starts at 0, A goes to 10, incrementing both variables in between. The only difference here now being bottom tested. So I think your control flow graph here should be fairly similar to the other two, with maybe one small difference. Here is what I would probably have written, and here's what I expect our IDA graph to look like. Set A equal to 0 up at the top. That flows into the loop body block, which has B++ and A++. That flows into the if A is less than 10, although I suppose these could really be one block together, couldn't they? I drew those as two separate blocks, but there's no reason that couldn't just be one block there. If A is less than 10, in the true case, is going to go back up to the top of the loop body, and in the false case is going to fall into the return 0. So let's again open this up in IDA, and actually I'm going to do a side-by-side comparison again, because I think there's something else instructive here. So we'll do new instance. Let's open up 2 again. Perfect. Okay. So, on the left-hand side, this is our for/while loop. I genuinely don't remember which one it was for a while, but it doesn't matter, right? It's one of those. On the right-hand side, I have our do-while loop. Now, as far as the graphs are concerned, these look quite different. Well, a little bit different, right? We definitely have a bottom-tested loop on the right-hand side, where we put 0 in the register at the beginning, have the loop body with the comparison that jumps back up to the top, and then in the false case, falls through to the return. So how many people got that one? Should be pretty easy. So here now, let's take a look at the linear disassembly of the two of those, and let's see what we notice. So I'm going to hit spacebar on both. Oh, not that. There we go. And there's our for/while loop, and here's our do-while loop. Look at these for just a moment and see if you can tell me if there are any differences between the two. Let me see if I can zoom in without losing both of them. Hopefully. Oh, nope, I guess not. Okay, sorry everybody. It's going to be small text on the screen. See if you can tell me what the difference is between these two now. There is a difference. Yeah, it's just the jump. The only difference between these two bits of code, other than I guess the labels that IDA has inserted that aren't technically in the code but IDA has annotated, the only code difference between these two is the jump, right? So here's maybe another reason that the compiler likes to structure everything as a bottom-tested loop, is that all it has to do to make that a top-tested loop is just insert a jump at the beginning. So I think that's kind of an interesting I don't know, property of the compiler, right? So we have about 10 minutes left here. I want to now have you do the same thing in reverse. I'm going to give you some IDA graphs, and I want you to see if you can write what you think the C code to produce those would be. So I will zoom in on this for you. So there's an IDA graph, either on your paper or on your computer if you prefer, whatever is easier. I want you to see if you can do the same thing in reverse. try to write up the C code that would produce this graph. And I suppose, remember, you can probably ignore the majority of the boilerplate code at the beginning, right? You're not going to write the get PC func AX function.
So you haven't initialized your variable anywhere?
Actually, no. You're right. I didn't. Good eye. So clearly there's a local variable being used, but it was never given a value before being read. This is kind of a toy example, right? This code doesn't do anything useful, but yeah, good eye. There was no variable initialization.
Not hiding it there?
It shouldn't be.
Okay.
Okay, let's see what C code this probably was. Maybe? I guess I have to single finger scroll here. Okay, that is the C code that I used to produce this graph. Who got exactly that? Even down to the variable name? Did anybody write int A? Nice. So that would be impossible to know, right? It could have been called int supercalifragilisticexpialidocious, but here it is called int A. Sorry. Next example. So again, see if you can figure out the C code that produced this.
What's that?
So, yeah, you may notice that there's a lot of similarity in the first 5 instructions on all of these. This is just sort of compiler boilerplate. The first 2 instructions are our prologue. This reserves space on the stack for local variables. Although we only have 1 local variable in C code, the compiler has reserved 16 bytes, I think just to preserve alignment. And then the call get PC func AX and add EAX. I think this is related to position-independent code structure. Like, it's giving it the ability to find its values in the data segment without knowing their direct address.
Gotcha.
Something related to that.
Got it. Got it.
Okay, let's check out the C code. Let's see what we've got. Okay. Here is the C code that I used to produce this graph. In this case, I remembered to initialize my variable first. So we have A equals 9. Here the move EBP plus var for 9 is A equals 9. We have a do while loop. You can tell this is a do while loop because the comparison and the jump is at the bottom, and there's no jump to that immediately, right? We fall into the loop body first. We can see that we're subtracting 3 from A with sub var for 3. Then we compare A to 0, and in this case, the condition does not get inverted because we're jumping back up to the top into the loop body when it's true, so we get the same condition as this. Was anyone able to produce that exactly? Anyone get close? Close is good. What differences? Oh, okay, well that still counts.
Int A equals 9, but I have declared it on the same line as initializing here.
Gotcha, yep. So, I mean, right, structurally that changes a little bit, but as far as what the program does, not a big difference. So I'm gonna give you one more. I realize we only have 1 minute left. Is it okay if I give you one more example? And then we'll stop and give you a break after that. Here is your last example. And let's turn on the Zoom again. Whoops, don't look, that was the answer. Okay, there's your last example. Okay, in the interest of time, I'm gonna put the answer up on the board, but feel free to ignore it, don't look at it if you're still working. I think this is a good one because this generated a lot of thought here. So, there it is. So I think whether you wrote this with a for loop or a while loop, it's still correct either way, right? There's no way to tell. Couple of things that make this one more complicated. We have a control structure nested inside of another control structure if inside of a loop. And also, did anybody notice there was a different variable being used? You had a var4 and a var8, so that's a little tricky. Oh, did I mess that up? Hold on. Subtract var4, oh my goodness. What the heck? I have an error on my slides. My apologies, folks. Yeah, clearly, what? So there's a var4, there's a var8, but these are both subtract. I think that I have a problem. I think my loop, wow. Okay, well, I apologize. Mea culpa. That should be an A minus minus, and then I think we're good. So I'm going to stop there. I think this is a fun way to build intuition about what compiled assembly code looks like at the C code level.